started for today. Looks like a thinner attendance than usual. I do have a few extra handouts from the last two times. If you're missing a handout, feel free to come up and take a look. There's a 1, 2, 3. So very quickly, I'll kind of review what we've covered up until this point, and then I think today we'll just finish off the stiffness method for beams. So last time, what we did basically was to come up with this. All right, let's wait a couple minutes again for you to get settled. All right. So as I mentioned last couple of lectures, that we are trying to solve problems with beam elements where the degrees of freedom for a beam element are displacements, the transverse displacements, and the rotations at the nodes. Okay, so the first job always in a beam problem is to try to discretize or try to divide up your beam structure into different number of elements, nodes, and so on, and then try to assemble what we have called the force. This is the force and moments. So this is the force vector in general, and this is the displacement degrees of freedom for a beam element. And initially, we started out trying to find out what this 4x4 matrix would be. And what we said was that if we are able to figure out the response of a beam element in these 4 different mode shapes, okay, so these are 4 different deformation shapes, which we are going to call cases 1 through 4. We found what was the response in case 1, found what was the response in case 2, and I pointed out that case 3 and case 4 are just mirror images with sign changes of case 1 and 2. So using all of that, last time we were able to come up with this 4x4 element force displacement relationship. We have forces and moments on the left, degrees of freedom on the right, and all of these stiffness coefficients tell me that how is a beam element going to respond, meaning what would be the forces and the moments needed at the ends of the beam element to ensure that these are the degrees of freedom in force. So delta I, delta J, theta I, theta J, relating all of those 4 quantities. So that's where we were about last time. And I pointed out to you that that this is the same relationship that we had for the truss elements, which was, for truss elements, it was extremely simple because that truss element response depends only on the change in length of the element, right? That was the +1, -1, -1, +1, very simple 4x4 relationship. Even this relationship is constant. That relationship never changes. So, but indeed, in this case, all of them are non-zero. For the truss element problem, you had only 4 entries which were non-zero. Here, for the beam element, everything is non-zero. Okay, so that's where we were about last time. Now, let me ask you a question. For the truss element problem, what did we do after we derived the force element displacement relationship? If I give you a truss problem, the first thing you compute is that +1, -1 thing for each truss element. After that, what do you do? Marisol, go ahead. Yeah, you put it in the global, but before that, you also have to transform it because truss elements may be inclined in some direction, in some random direction, right? Here, the good thing is there is no transformation needed. So indeed, what we'll do is we'll take these matrices and we'll put them in a global stiffness matrix of the correct size in the correct locations. And then we'll solve that global system of equations exactly the same way that we solve truss problems. So let's take an example for that. And On your handouts, there should be a MATLAB code um, with with the sample input file for this problem. So let me actually open up MATLAB and run through this code. Um, Maybe I can do that just as it is. So in the MATLAB files, this main file is called beam main 2d.m. It The overall structure of this file is extremely similar to the truss code that I gave you, but I'll point out the differences in a little bit. Here uh, on the handout, you should be able to see that for this particular problem, I have these three nodes with a 5 kilonewton load on the right. So three nodes means immediately I have 6 degrees of freedom. For this particular problem, how many degrees of freedom are free and how many are fixed for this particular problem? How about node 1? Degree of freedom 1, is that fixed? Yes. How about rotation? It's not fixed. How about 2? This guy is fixed. Rotation is not fixed. At 3, both of them are free, right? So there are 2 degrees of freedom that are fixed, which is degree of freedom 1 and 3, and the other degrees of freedom, which are 2, 4, 5, 5 and 6, they are free degrees of freedom. So for this problem, the input file also reads very similar to the truss problems. I have these 3 nodes. I have 2 elements in this case. There are 2 boundary conditions, both at node 1 and node 2. Degree of freedom 1 is constrained. Degree of freedom 1 is the transverse displacement, degree of freedom 2 is the rotation. So that's how you would read the input files. And actually that reminds me, in the online version on Blackboard, the file that I've posted, it's called beam1.txt. Maybe I'll show you that. So this beam1.txt, in the online version, I have one extra boundary condition. You that that boundary condition was left there um, um, from last year actually, but technically you should delete that, and this input file now is exactly the same as that in this handout. Okay, so I'll come back to that file in a bit. Um, so large parts of this program are exactly the same. You get the input. This line get beam data 2D is get input from that that beam1.txt. This is initialize your K global matrix U vector and F vector. Um, and then there is the similar sort of code that you saw in the truss element problem, that you figure out which degrees of freedom are free versus specified. So some degrees of freedom will be given to you, some will be free. You add the nodal loads to the force vector, and then you have this loop. This is the most important part of the code. This loop, which is again very similar to the truss element code, that you loop over all the elements in the structure, and you find out what is the K element. So this beam element 2D is the main beam element code, uh, and all that it needs is the locations of the beam nodes. It needs Young's modulus. It also asks for area, but um, area will not be used in the beam problems. When we come to the frame problems, we will need to use area as well, but I've left it in there just to be consistent between beam and frames. And we need the I, the moment of inertia of the beam problems. I'll go through this in a little more detail in a bit. And after that point, you assemble the global stiffness matrix. So I'll call that K global is equal to sum or some sort of an assembly of K M, where M goes from 1 to number of elements. So this is just an interpretation that you're adding up all of the individual elements into the global stiffness matrix, exactly the same way that we did for the truss elements. And after that point, it is uh, exactly the same command to solve, which is saying U is equal to K inverse F for the free degrees of freedom, and then you solve for the reactions at the supports, and you display them. And if you look at that main code beam element 2D that I was talking about, that beam element 2D code is just these 5 lines of MATLAB code. You calculate the K element stiffness matrix. This 4x4 stiffness matrix is coded up once and for all beam and frame problems, and this is exactly the same as what we derived. So if you look at this 4x4, which we obtained by combining all of those 4 cases, cases 1 through 4, once we've obtained this tells me the relationship between the forces, moments, and the degrees of freedom, which can directly be coded up into the MATLAB program, um, right here. Let's see, right here. So this was the 4x4 that we'll use again and again for no matter which beam problem it is. And what I'll do now is just to run you through an example problem of how MATLAB computes it. So for that, we'll go to the actual code. I'll go in here. I'll place a breakpoint at this line number 11, which is the read input data from that file. I'll also go ahead and save that change that I made into the beam1.txt. So let me save that. And now if I click run, MATLAB comes down to this, asks me for the name of the input file. I'll choose beam1, open. And at that point, I'll start stepping through the code. So now you'll see that I have the nodes vector. There are 3 nodes in this problem at 0, 2, and 4. There are 2 elements. 1 is connected to 2 and 2 is connected to 3. Simple enough. There's Young's modulus, which is the same, 200 gigapascals for both the elements. Area of cross section is mentioned, but again, it is not used anywhere in the beam codes. Okay. I, moment of inertia, is indeed used. So 0.5, 10 to the minus 5 is the moment of inertia. And again, these are in units that you have to be consistent with. So for example, in this problem, this is 5 kilonewtons, 2 meters. Everything in here, we are using units of meters for the length. And there is no mass or time or anything. So the only units are here for length. So you have to be self-consistent among all of those units. If you're using meters, use meters for everything else. So let's go back to the code. After this point, I'll kind of zoom through to that for loop. And up until this point in the for loop, what we have done is we have constructed an empty K matrix. So this K matrix is 6 cross 6 all zeros, which makes sense because there are 3 nodes, 2 degrees of freedom per node. The U is also all zeros up until this point because this is something that we'll be calculating in the last step, in the solve step. This F vector is also a 6 cross 1 where there's a minus 5,000 at the last entry. So minus 5,000 because we have a load of 5 kilonewton at degree of freedom 5 that corresponds to node 3. Aaron?
How would you apply a moment?
How would you apply a moment? You would say, for example, if I have a moment of 5 kilonewton meter at degree of freedom 6. You would just have in the input file, which I guess is also there in your homework 8, you have a 300 kilonewton meter moment. You just go to the input file. Let me go there. And in case of nodal loads, it says node 3, degree of freedom 1, I have a force of minus 5,000. So for a moment, what would you do? Let me put the question back to you. Right. So 3, 2, and whatever the moment is, positive or negative, right? So, um, so back to the code. So we have F, K, and U already in there. And now we are ready to begin assembling or begin creating the element stiffness matrices for these codes. So as I go through this element loop, I element, the variable is 1. It tells me that element 1 is connected to nodes 1 and 2. The next line calculates the X and Y locations of those two nodes. And then we give, or then we make a call to this beam element 2D subroutine. So for there, I will step in to that code. And clearly there is not much to do here. You just compute these 5 equalities and we are done. So these 5 expressions, as soon as you calculate these 5 expressions, you have this 4 cross 4 element stiffness matrix for element 1. Now, for the truss elements, that relationship was very simple. You can easily write by hand. So for homework 8, make sure you write out the values, but also compare it with the Matlab codes that I've posted. And the point of that exercise is just to make sure that you're following where did that element stiffness matrix come from. You can and you should use Matlab to do all the computations. Don't compute. I would suggest don't compute all of these things by hand on your calculator and so on. You can assume we'll assume that you can do that. April.
So looking at the homework,
Say that again.
looking at the homework,
Uh-huh.
a lot of the problems have different I values.
That's right.
So how do you get the stiffness matrix to consider two parts of the
Sure. So let's see what this beam element subroutine does. For this beam element subroutine, all that it needs is the locations of the two nodes. It needs E, the Young's modulus of that material, and it needs I, right? So if I have an element 1 that has one I value, an element 2 that has a different I value, that will automatically be taken care of here. All that you would have to do is what? Is to specify the correct I value in the input file, which is right here. So look, element 1 is connected to nodes 1 and 2. Its Young's modulus is 2 gigapascals. Area doesn't matter. And the I value is given here. For element 2, you can use a different I value here. That make sense? And this code will automatically take care of that because you're sending in the correct I value to the subroutine. So let me go back there. All of these I values are for this particular element that we are talking about. So at this point, all of these things are computed. K element is obtained, and we go back into the main code, find out the element degrees of freedom for this element, which would be 1, 2, 3, 4, because it's nodes 1 and 2. And let's take a look again at the global stiffness matrix, where what components of this matrix would change when I assemble it in here. What elements of this global stiffness matrix would change when I assemble the K element for element 1 into this? Hongzi? Yeah, the first 4 cross 4 would change, right? Because just as I showed you, the element degrees of freedom for element 1 are 1, 2 for node 1 and 3, 4 for node 2. So it would change the first four cross four, and I'll show you that. I've executed that statement, and now you can see that indeed that's the change for element one. Um, Let me ask you another question. So at this point, I'll go back here, calculate for element 2. It is connected to nodes 2 and 3, and I have the nodal locations for that. And before I go into this, let me ask you this. I've just computed the K element stiffness matrix for element A. Can anybody tell me what would be the element stiffness matrix for element B? Miles? Exactly the same. Why is that? Same dimensions, same material properties, same E, same I, same everything, right? So let's look at that. If I go back to this 4 cross 4 that we derived, all that it depends upon is E, I, and L, right? And if E, I, and L are the same for two elements, you're going to end up with the exact same 4 cross 4 stiffness matrix. But of course, Matlab doesn't know ahead of time which elements would be the same. So you go ahead and compute that, but I won't go into that code again. You get the exact same stiffness matrix. Which degrees of freedom will this element 2 change in the global stiffness matrix? So the global stiffness matrix looks like this right now, which has element 1 in there. Which degrees of freedom would change for when I put in element 2? 3, 4, 5, 6. And the way we decide that is by looking at the connectivity of the element. So this variable that I call LDOFs, this tells me that the element degrees of freedom are 3, 4 for node 2, 5, 6 for node 3. And essentially, the bottom 4 cross 4 is what is going to change there. So let's execute that. And indeed, that's what gets changed. And at this point, there are no further elements in the problem, so it exits the loop. And at that point, we are solving exactly the same system, K free max slash F minus KU specified. And maybe I'll write that in the, I'll write that up here in the sample code. So this obviously also tells you that Ka is equal to Kb, which is what we calculated. The global stiffness matrix is what we have just calculated. We have the load vector already in there. The degrees of freedom, degree of freedom 1 is fixed to 0. So that is known to me. Degree of freedom 2, which is rotation, is not known. Degree of freedom 3 is 0, which is vertical displacement, and all the other degrees of freedom are free. So 3 question marks. Essentially, we have 1 and 3 fixed, and 2, 4, 5, 6 that are free. So in order to solve this system, K times U is equal to F, where some of those degrees of freedom are free and some are fixed. How do we do that? We use exactly the same set of equations that we had before. Let me see if I can pull that up. Solution right here. So some of those degrees of freedom are free and some are fixed. We will use exactly that logic to solve this system of equations, where we break this up into free and specified. And it is exactly the two same lines of code in Matlab. These two lines, 53 and 54 in this beam code, which will allow us to solve. So let me show you that too. Right now, U is all zeros. As soon as I execute this line, I have the correct displacements at all the degrees of freedom. So this is displacements and rotations, right? Degree of freedom 1, 3, and 5. This degree of freedom 5 is the vertical displacement at node 3. The other 3 degrees of freedom 2, 4, and 6 are rotations at those nodes. So knowing this degree of, knowing the displacements, I can go back and calculate the reactions from the second equation. Um, and now I have the unknown reactions as well. Or this is the external force vector on the structure. So you remember this 5 kilonewton force at degree of freedom 5. This is the reaction at node 2, and this is the reaction at node 1. Okay. So once you have that, the rest of this is basically just plotting the output. So I'll run through that and let's see what is the response we get. So figure 1 shows me the deformed shape and the reactions from the code. Remember, we have 5 kilonewton here. The reaction is 5 kilonewton up. Sorry, 5 kilonewton down there and 10 kilonewton up in the middle. Just based on those degrees of freedom, we can plot this deformed shape and the reactions that we had computed. And figure 2 also plots the shear force and bending moment diagrams for this beam. This I'll go through in a little more detail. How do you think we can compute the shear force and bending moment diagrams for the beam problem? Now that I know that the displacement vector is this, the reaction force vector is this, how can I calculate the bending moment and the shear force diagram for this beam element? So just as an analogy, the bending moment and the shear force diagram for a beam element is very similar to the internal force in a truss element, right? In a beam element, the shear force and the bending moments are internal forces and moments. How did we calculate internal forces in the truss problem? Anybody remember? So for homework 7, was it? Or yeah, homework 7, when you had to calculate internal forces for truss elements, how did you do that? And I think part of it you have to do it by hand. Anybody remember? So go ahead, Napo. Say it again.
Change in length.
That's right. You're trying to find the change in length of the element. How would you find the change in length of the element? If you already have the displacements of all the nodes, you use that to find the change in length of the element for the truss by picking out the degrees of freedom for that truss element. You remember, let's say if I have 10 nodes and one truss element is connected to nodes 2 and 5, for example, then you would pick out those 4 degrees of freedom from the global displacement vector. You would transform them to the local axis, which would tell you what the change in length was. Once you have that change in length, you multiply that with AE over L, and that would be the internal force, right? Which is basically doing K element times U element. The good thing about beam problems is that everything is horizontal. So you don't need to do any transformation at all. You just go to element 1, for example, to this element, find out what is the element degrees of freedom. So I'll do that maybe on the screen. So I have my global displacement vector, which is a 6 cross 1. Out of this 6 cross 1, what are the degrees of freedom associated with element 1? Don't you? The first 2 nodes, but which would be the degrees of freedom associated with those? So nodes 1 and 2 are associated with 1, 2, and 3, 4, right? So the first four of these four values are degrees of freedom for element 1, and the last four are degrees of freedom associated with element 2. So I'll store them in a separate variable. I'll say UA, degrees of freedom with element A are U of 1 through 4, and KA is the same as the K element that we just computed because both of the elements have exactly the same K. So if I calculate KA times UA, if I calculate KA times UA, this is the internal force vector. What I've just done is exactly computed this relationship. I had that K element 4 cross 4. From the global solution vector, I picked out the 4 degrees of freedom for element 1 and multiplied K element times U element to get forces at the two ends. Right? All I did there was multiply K element, KA times UA to get the 4 values at the ends of the beam element. Knowing these 4 values at the ends of the beam element, can you tell me what the shear force and the bending moment diagram would be? So if I tell you that there's a force here at QI pointing in the upward direction, is that QI the shear force on this beam element? Right? That is the shear force at this on this element. How about this QJ? Would that be the shear force or negative of the shear force? It would be the negative of the shear force because on the right hand side of a beam element, we assume positive shear force is pointing downwards, correct? So QI on the left is the shear force, QJ on the right is negative of the shear force. Okay. Similarly for bending moment, is this MI the bending moment at the left, or is it the negative of the bending moment at the left? Negative of the bending moment at the left. MJ on the right, is that positive bending moment or negative bending moment? Positive. So knowing these 4 values, which we calculated by simply picking out the 4 degrees of freedom from the global solution vector, multiplying it with K element, I got these 4 values. Now I can draw the shear force and the bending moment diagram. So going back to this, here. So I have this, sorry, this is the 4 cross 1 where I have the first element is Qi, second element is Mi, third element is Qj, fourth element is Mj. Now we just said that Qi is the shear force at the left of element 1, so that's why my shear force is starting out at minus 5,000. Qj is the negative of the shear force at the right end, so the correct shear force would be negative of this 5,000. That's why I still have minus 5,000 up here, right? Now, so let me mark that actually. This Qj has to have a negative sign, and we also said that Mi has to have a negative sign, correct? So the bending moment at the left end of element 1 is 0. Bending moment at the right end of Mj is minus 10,000, right? So Mi to Mj would be a straight line. It would go from 0 to minus 10,000. That's what we have here. Similarly for element 2, if I do Kb times Ub, I get again Qi, Mi, Qj, Mj. And this is the type of problem that I can give you, for example, on the final exam as well. I could give you the solution vector. I could ask you to draw the shear force bending moment diagram, right? Where you would need to realize that Qi is the shear force. So 5,000, positive 5,000, it jumps up to 5,000. Mi is negative. Qj is negative. So negative of 5,000 remains to positive 5,000. So clearly that's the shear force diagram. For the bending moment diagram, we know that Mi here, as it is, since it's given as 10,000, we would take the negative of that. So we start out at minus 10,000 and we go back up to 0. So going from negative 10,000 to 0 would be the bending moment diagram for element 2. Okay, so that's the only thing that you need to be careful about when you're drawing the shear force bending moment diagrams based on the stiffness method. On the stiffness method, in the stiffness method, as I mentioned, this Qi is equal to the shear force. Qj is negative of the shear force. Mi is negative of the bending moment. And Mj is equal to the bending moment. So the second element and the third element is where you would need to have the negative sign to draw shear force and bending moment diagrams based on the stiffness method. Okay. Questions, Miles?
So I just want to make sure that output is that given like the convention, or do you have to multiply them from one?
No, you do have to multiply by negative. Actually, the code itself will compute the correct value, and you can see that it actually plots the correct shear force diagram and 0 to minus 10,000. So I'm just combining those two diagrams all in one because so the shear force and the bending moment diagram, the code will already take care of that negative sign. But you have to realize that when you have to do it by hand, that's those two entries need to be multiplied with a -1 to get the correct shear force and bending moment.
So if, like you said, you gave us the output on the final exam, would that be already from the code?
No, yeah, so that output would be from the code. Let me show you the main output. So I would give you this solution vector, for example. Then you would potentially have to pick out the 4 degrees of freedom corresponding to element 1 or element 2. You would have to multiply k element times that 4 cross 1 u element, and you would get, and then you would get this 4 cross 1. When you multiply that 4 cross 4 with that 4 cross 1, you would get this 4 cross 1. And you would have to manually take the negative of this value and the negative of, so the negative of the second and the third values. You would have to manually do that to be able to draw the correct shear force and bending moment diagram. Make sense? Okay. All right, so let me do a quick second example. In this example, I think this is one of the examples in your book, but I would rather not use the methodology that's given in your book. You can easily use the codes that I've given you to solve this problem. But so this problem is again pin, roller, well, roller, and pin. And it says that support B, the middle support settles down by 1.5 inch. There is a load 20 kilonewtons up here. Find the reactions and draw the shear force and the bending moment diagrams of the beam. E and I are given to you. So how should we proceed? First of all, if I gave you I have given you the Matlab codes, and if I asked you to solve this problem, how do you do it? Yeah, we try to come up with an input file for this. So for this problem, how many nodes should I have? 3 or 4? 4, well, because there is a load in here. Technically, you can do it with 3 also, but I'll talk about that a little bit later. For the code that I've given you right now, yes, you do need at least 4 nodes. 1, 2, 3, and 4. Okay. Let me ask you this. What if I create an additional node here? So 1, 2, 3, 4, and 5. Can I do that? And would that help me at all? That's right. So it wouldn't help me technically with this particular problem. Um, it's entirely up to you how many nodes you want to create. There is a minimum number that you need to be able to solve the problem. But if you create more nodes than that, then it's not wrong. It just means that you'll have to do a lot more work. Not you personally, but probably Matlab would have to do a lot more work. There would be lots of elements. The stiffness matrix size will be much bigger, and you will get displacement and rotations at all the intermediate points wherever you create a node, which for this problem, the way that the question is framed, is not necessary. Now, that said, I should also point out that in general, for these types of problems where you have, this is a beam element problem, this methodology of the stiffness method is based on very similar concepts as what we call finite element methods, where if you have more elements within your problem, then you get a better or more accurate answer. Okay, so in general, you should keep that in mind, that if you, for example, if you go out to your first job and you're modeling some structure, and if you have to choose a number of elements, if you choose too many elements, then you will bog down the computer. If you choose too few elements, your answer might not be accurate enough. So you have to do a little bit of a balancing act there. But for this particular problem, yes, at least we need these 4 nodes. So I'll create those: 1, 2, 3, and 4. And the degrees of freedom for those would be 1. Sorry, not that. So 1 and 2, 3 and 4, 5 and 6, 7 and 8. 8 degrees of freedom, which means that our global system, K global, would be what size? 8 cross 8. So we'll start out with an empty 8 cross 8 and we'll fill in all of these elements. How many elements do I have? I have element 1, element 2, and element 3. Clearly, element 1 and element 2 should have the same stiffness matrix, right? Because same length, same E, same I, same everything. So both of those elements should have the same stiffness matrix. And if you run through the code, this is the stiffness matrix that you would get. 4 cross 4 stiffness matrix for both K1 and K2. For element 3, you would get a different stiffness matrix. And at that point, you would assemble them into that big stiffness, global stiffness matrix. And hopefully we can identify the first 4 cross 4 comes from element 1. Second 4 cross 4 comes from element 2. Am I making a, okay, yeah, I included one more. So let me move this here. Thank you. So the second 4 cross 4 would be from element 2. And finally, the third 4 cross 4 would be from element 3. And of course, when you're assembling, you are adding the overlapping elements. Once you have the K global stiffness matrix, you solve for the displacement and the force vectors as usual. But here, keep in mind that that node 3 settles down by 1.5 inches. So if you look at degree of freedom 5, node 3 degree of freedom 5 should have minus 1.5 in there. And indeed, that is a specified degree of freedom that's known to me ahead of time. And maybe what I'll also do is I'll go to the MATLAB code, run it. And this is, by the way, in input file number 2. So the input file number 2, as you can see, it says the boundary condition at node 3 in direction 1 is negative 1.5. So if I run this, I'll stop it here in this problem. So run and choose input file number 2. And at this point, you can see that before solving, I do have the correct specified degrees of freedom in there. All the other unknown degrees of freedom are 0. My force vector before solving is just that 20 kip force on degree of freedom 3. And K is this big 8 cross 8 that has already been constructed in the previous loop. So in that previous loop, it was already constructed. Now, if I solve it, you have to keep in mind that this part of that line 53, which says K dot free K dot spec is times U spec. Basically, if I go back to that solution line, most of the times your specified degrees of freedom are 0, right? Most of the times you say that this degree of freedom is fixed. So specified degree of freedom is 0. If it is non-zero, then you do have to add or subtract something. So that if it is 0, then it goes away. There isn't any trouble. But in this case, since there is support settlement, that would be non-zero. And therefore, when we solve it, we get the degrees of freedom at the rest of the points. And at that point, you calculate the reactions as usual from the second row of that solution. And then I'll just let it run out. And I have my response, figure 1. I have a support settlement of 1.5, load of 20 kips, reactions are pointed out. And using that same logic of Qi, Mi, Qj, Mj, you can also plot the shear force and the bending moment diagram. So shear force is 12.23 up here, drops down by 20, goes to -7, goes up by whatever that amount is, and goes back to 0. Bending moment, of course, should be continuous, and it is indeed like that. So that's just another example of a system where you have a support settlement. Okay, so next time what we'll do is we'll solve problems which have distributed loads, and I think with what you have today from the lecture and the MATLAB codes posted, you should be able to complete homework 8. I will also point out one more thing. I think maybe some of you are struggling with this matrix algebra. So I don't really want to cover any matrix algebra in this class. If you don't remember what you might have done in linear algebra, I'll post a set of notes online on Blackboard for you to be able to look through some basic concepts on matrix algebra. And if you have your book, there is an appendix in here. There's an appendix in here which also talks about uh, basic properties of how you work with matrices, how you multiply matrices, how you take inverse of a matrix, and so on. So if you're having trouble with those concepts, I'll post some notes online. And if you have questions, again, post them to the Blackboard. So I'll see you all on Friday.
For this example, these would be the two that I'm going to
So actually, this is the global one. So you would, for example, so this is the global solution vector, and this is the global force vector. If you are trying to compute, let's say for element 1, you would pick out 1, 2, 3, 4. So that 4 cross 1 you pick out, you would go to the element stiffness matrix of element 1, that's K1. Do that K1 multiplied by U1, and you will get another 4 cross 1. So that 4 cross 1 you would have to do so you don't do that on the global force vector, you do that on the element.